Okay, so now we're going to talk about a concept called specific heat. And specific heat is helpful in a few different ways, but in particular it's helpful just in thinking of in terms of how much heat an object can hold. Okay, that's probably the best way to think of it. How much heat can an object hold, right? So high specific heat of water helps keep temperature more moderate in summer and winter. So you find that towns on the coast have more moderate temperatures than towns that are inland because water is a great reservoir for heat. It can either offer heat if the air is too cold, or it can absorb heat if the air is too hot, right? So this is really nice. Now our learning goal here, let me back up here. Our learning goal for this section is to use specific heats to calculate heat loss or heat gain, right? And we'll make more sense of it later. All right, so first of all, again, specific heat is defined in the following way. Specific heat is the amount of heat that raises the temperature of exactly 1 gram of a substance by exactly 1 degree centigrade, right? So how much heat does it take to increase the temperature of 1 gram of something by 1 degree centigrade? That's its specific heat. It's different for all substances, okay? And it has the units of joules per gram degree centigrade. Sometimes we say calories per gram degree centigrade, right? So we use both of those. So in sort of a formula way, we might look at context. We might look at specific heat like this. Specific heat is the heat divided by the grams per change in temperature. Okay? So the specific heat for water, for example, is 1.00 calories per gram degree centigrade. That means it takes 1 calorie to raise the temperature of 1 gram of water by 1 degree centigrade. That's the specific heat of water. Now, since there's 4.184 joules in a calorie, you can see that those two would be also true. So some specific heats of some particular substances. This is kind of interesting. Aluminum, it takes 0.214 calories to raise a gram of aluminum 1 degree centigrade, right? So that means that it doesn't take much heat to change the temperature. And so aluminum is going to fluctuate a lot more than water, right? Water's 1 and aluminum is 0.214. So that means that if you give the same amount of heat to water, it's going to take a lot more to change the temperature of water. That's why it's such a good reservoir for heat. Aluminum, not so much, right? Copper, even less. Look at that. 0.1 calories per gram degree centigrade. And this is 1. So it takes 10 times more heat to raise the temperature of water than it does to raise the temperature of copper. And that's why copper and aluminum are good to bake with, because they're so low. Gold would also be good. That's even lower yet, except gold is so expensive. And silver would be good to cook in, except silver is so expensive, right? So copper is really good because you can transfer the heat from the flame of the stove to the food very easily. All right, so let's do a learning check now. When ocean water cools, what happens to the surrounding air? I'm going to encourage you to pause the video and look at these 2 questions and then come back. All right, so let me suppose that you did pause the video, and I'm going to walk through it with you. When ocean water cools, the surrounding air gets warmer, right? And that's because the ocean water is taking the heat out of the air, okay? Sand in the desert is hot in the day and cold at night. Sand must have a very low specific heat because it doesn't take much heat to change its temperature, right? And that's what that's about. Okay, so let's talk about specific heat in terms of calculations. So the core chemistry skill is we want to use the heat equation. So the heat equation looks like this. Heat is equal to mass times the change in temperature times the specific heat. Or in other words, heat is equal to M times delta T times SH, okay? So we let's do a learning check. I'm going to actually write this out. Heat, I'm going to oftentimes use Q for heat, is equal to M delta T times specific heat. That's the formula we're going to use. Let's do a problem with that. Okay, I'm going to encourage you to pause the video and do this problem. So we want to know what is the specific heat of a metal that requires that much to change the temperature that much. I'm going to pause you pause the video and then come back and do this with me. Okay, so let me suppose that you did pause the video, and I'm going to write the equation out. Q is equal to M delta T times specific heat, right? This is the same equation if I divide both sides by specific heat, or rather by mass delta T. I can say specific heat, I'm going to rearrange this in a couple of things, right, is equal to Q over M delta T. Right? Can you see what I did? I just divided both sides by this term, right? And I isolated specific heat. And I did that because I wanted to know what is the specific heat, right? That was the question. So let's fill in all the answers and we'll be done. The mass is 24.8 grams, right? I'm going to put the units in a different color. 24.8 grams, right? And the change in temperature, that looks like it's going for 24.5 minus 20.2 is 0.3, 4.3, okay? So that's going to be, the change in temperature is 4.3 degrees Celsius, right? And energy is 275 joules, right? So it's going to be 275, oops, let's get that in the same color, joules, and we're going to find that whatever this is, it is joules per gram degree centigrade, because there's my units, right? Joules, grams degree centigrade. So I'm going to take 275, here, 275, and I'm going to divide it by 24.8, and I'm going to divide it by 4.3, and I'm going to find that my answer is 2.5787. 2.5787, but I only have 3 sig figs that I can use. Only 2 sig figs there, right? See that? Look at that. 3 sig figs here, 3 sig figs here, and 2 sig figs here. So I have to report this in 2 sig figs. So I'm going to say this is about 2.6 joules per gram degree centigrade. All right, hope that's helpful. And we'll be using specific heat more in upcoming sections.